Morning, this is Dr. Irani. Welcome to the last lecture for this class. Today, what I'd like to do is essentially give you a lecture which describes an actual internship which was done in 2005. This was an undergraduate student of industrial engineering at the Ohio State University. Her name is Meena Stansel, and she had essentially taken all of her classes, and then she took the two classes I taught. They were connected to each other. One class was facilities planning, the other class was production control and scheduling. And as you know, value stream mapping essentially connects facilities planning and production control and scheduling. So she had taken all these classes, and then in 2004 I had received a grant from the Forging Defense Manufacturing Consortium. And what that grant essentially required me to do was to implement job shop lean in custom forge shops. So 2005, we had SIFCO Forge Group approach us and say, look, we like what you're doing and we would like to host an intern. And so it was pretty much that Meena was the best candidate I could send to them. At that time, I was basically a professor at Ohio State, and so she was full-time at SIFCO. And you will see that she did just an amazing amount of work. Just full credit to her. And I hope that this lecture and what she did becomes an inspiration for you, that when you get hired as interns, I know that this summer things look challenging, but don't worry, I'm sure things will come around. I know of at least 3 companies which have expressed interest in interns. So we'll worry about that later. What this lecture does essentially is to walk you through what the entire course has taught you. And step by step, it implements this thing called the quick start approach to job shop lean, which effectively is essentially lean for high mix, low volume. You must have seen probably in all the projects that you did that you could not really assume one product and try to do too much with the assumptions that value stream mapping forces on you. Okay, so with that, we shall start the lecture. So here's a quick overview of the SIFCO Forge Group. They were located in Cleveland, Ohio, and they pretty much are custom manufacturers. They forge the parts and then they machine the parts and provide them to pretty much aerospace customers. You see that? So at that time, I think Sikorsky, the helicopter builder, was a big customer of theirs. But you can think of pretty much all the aerospace primes, Lockheed Martin, Raytheon, and they would probably be making parts for them. And you can see they're a forge shop. So all of these machines, sorry, but they're all monuments. And you will quickly see as the presentation unfolds that they just grew by adding equipment without any plan of how the equipment should be located to have good flow. And you've seen pretty much throughout the course that if you have not designed the layout for good flow, even if it's not one piece, but at least visual communications, small batch movement, dynamic ranging material handlers, if you have not designed the facility layout and you do not operate the layout with a view to be quick in the flow, you can do all other improvements, but eventually they will all get compromised. So here's the scope of the project. Basically, what the executive said was, tell us what this thing job shop lean is. We've been doing lean, we've been doing 5S pretty much, and we've done some setup production. We've got the morning huddles. We've got the basic things going, but we know that we're a job shop, and this job shop lean thing seems to be of interest to us. So that was the first goal. Second was give us some training. When the intern comes in, could she give us a few lectures? And maybe could you give us some of your lecture material so that she can then discuss some advanced concepts with us. Could she work with this team? Could she work with our team so that they get a sense of, oh, yeah, this stuff applies to what we do. And then, can you give us an example of the job shop lean thought process in action? And how do you apply that thought process to assess problems and generate solutions? Well, in all honesty, the quick start approach is almost uh, a copy of the whole value stream mapping approach, but what we've done is thrown in theory constraints as a focusing aspect of the project, and also tied in classic industrial engineering tools like flow diagrams, flow process charts. Uh, and I think it's important to understand that we did not take lean as something totally different from industrial engineering. We blended the ideas together. So at a high level, this is the comprehensive approach to job shop lean. This is where you take the entire product mix, you run them through fast, you get the part families. Once you get the part families, then you decide to pick a part family because you would like to implement a cell, either a physical cell or a virtual cell. Then you go through the entire process improvement methodology that uses Six Sigma or industrial engineering or theory of constraints. Doesn't really matter. But the idea is that you kind of reach the point where you design the cell and then you schedule the cell and then you try to create like an autonomous working unit. Then, if you think that other part families exist, you go back up here and then you repeat the process. Fundamentally, what job shop lean does that lean doesn't do is just essentially use things like cluster analysis and capacity planning to look at designing a mini job shop. So you're not designing a one-piece flow cell. Okay. So that's the comprehensive approach. This is the quick start approach, and I will do my best as I go through the lecture to refer back to this particular slide and show you how each of these steps was executed by Meena. And again, I wish to give her full credit. All that I was doing was guiding her remotely and made a couple of visits to Cleveland. But other than that, this is what I think any of you, if you really put your mind to it, with your education at the University of Houston, plus what you're learning from me in the classes, you can do this. And within 3 months, I think you would have a pretty good result. Okay. So this is pretty much the quick start approach. And you will notice that really the key point of difference from the typical approaches of pick apart and do value stream mapping is I form product families and then pick a representative part or parts inside of that part family and then go through this process which combines industrial engineering tools, lean tools, Six Sigma, theory of constraints. So that's the first step, data collection. So we collected data from about 2003 to 2005. And as you know, the production flow analysis software, which we still use to form product families, requires you to collect just 4 basic pieces of information about all the products. So you get each product. Now, in this case, these were forging, so there was no need for bills of materials to determine assemblies. You find the quantity that was produced in this period, 2003 to 2005. So they get multiple orders for the same part. Well, because they're a job shop, they don't get large orders. So it's always like in a make to order, deliver by due date scenario. For each part, then you collected the quantity, then you got the sales dollars. So when I sold 1,000 pieces of this part, I made $10,000. Okay. Profit margin is something normally people did not give us because we were outsiders. So they kind of basically said, okay, this is how much money we sold those parts for. And this is the routing. This is the DNA. This basically tells me that this particular part goes through all these work centers in this particular facility. Okay, and then we had the work center number and all the machines inside of it. Workstation cycle times, we do need them, but not immediately. And then we had, for each machine, how many people were needed because these were pretty big machines. So that's the first step, collect data from the past, revenue, quantity, routing, okay? Then we of course got all the routings, that's the next step. Now the step is, we have to create product families, right? So In this case, you create the input file for FAST. And then, FAST is essentially a collection of algorithms, and it's biased towards facility layout. But then, because a lot of lean has to do with material flow and facility layout, it basically does this whole battery of analyses. And then, depending on what you wish to do, uh, you use individual analysis. So once you get this data, then you do something called segmentation. PQS analysis is P stands for the products, Q stands for the quantity, dollar stands for the revenue. It's like a Pareto analysis, but it considers it in two criteria, both quantity and revenue. And you can see that out of about 700 parts, the PQ analysis said, you know what, 250 parts represent about 80% of not only total revenue earned during that period, but also total quantity, total number of piece parts produced. Then you basically do what is called a cluster analysis. So it took all these 720 parts and then basically grouped them by usage of common sets of machines. And that gave us the part family information. So basically from the clustering, there were two part families which we found. One was part family 1, which had about 229 part numbers. We have not expressed this revenue information, it was kept confidential. There was the second part family, which of course had 24 part numbers, and they had a reasonably competitive revenue earning. So naturally, with the quick start approach, after you create the part families, then your task is you pick a part family with the highest contribution. And then you say from this part family, let us pick a part or parts which have the same route, right? So let me go back and show you. This is the input file. So you can see again, you've probably seen a previous presentation. So these are all your parts. So the first column is the part number. Description, again, we deleted that because we had to protect the part information. These are defense parts, but that's the quantity and the sales information, right? So that's first thing is you get the part information. Then you get all the work centers. By the way, let me just go back. Bear with me, please. But you see how many parts we could look at because we're using, computer methods that are now taught in a typical degree program for data science. There were like 720 part numbers. Okay. Now you get the work centers. So these are all assets. These are, when you look at the routings, these would be the different machines that would be showing up in the routings. Okay, so if you go down here again, look at the number of individual work centers. There were almost like 98 work centers. These were physical locations that different parts went through. So once again, you can see that it is important not to get too stuck with the method of value stream mapping, because the value stream mapping just draws one part number and one routing. And that too pretty much works at the assembly level. With what we learn in industrial engineering, with the software we have, we can go way, way more complex. And then finally, you have the routing. So if you look at this routing, you have the part number, and then this particular part number, 00870D, it goes through these 18 steps. Each of these steps has a work center number, and there's a work center description. So that was essentially the input data for FAST. So then comes the cluster analysis, and there are lots of clustering algorithms out there. Again, I think some of you have taken the data science class in the department, so you may have an advantage. You probably have heard about cluster analysis. It's basically something called unsupervised learning. I think that it's again a very hard problem to solve, so they use heuristics, but unless you do this unsupervised learning, you are not going to go to the next step, which is classification using, say, neural networks or multivariate regression or decision tree algorithms. So here's basically a part of the cluster analysis solution. So remember we talked about PQS analysis? So if you go up here, this is basically what is called the PQS analysis. So the x-axis is the revenue, The y-axis is the quantity. And look, this is what you see as classic high mix production, especially in job shops, that on the revenue axis, if you said, okay, to the right of this point is high revenue and to the left of this point is low revenue, on the y-axis of quantity, you said, okay, here's a point, to the top of it is high quantity products, below that point is low quantity products, then you got what are called four segments. So high revenue, high quantity products, low revenue, high quantity products. Then you should have low revenue, high quantity, low revenue, low quantity, high revenue, low quantity. You basically get four businesses under one roof. And that is why, when you work with forge shops or machine shops or injection molding shops, or even companies like Ensinger Polymers, uh, they are trying to manage multiple businesses under one roof. So you cannot just take the Toyota production system methods and go back and apply them. You have to be more creative. And I think that's your advantage as industrial engineers. So if I look at the PQS analysis, it has sorted the products 1, 2, 3, 4, 5, 6 in the order of both aggregate revenue and aggregate quantity. So now I can simply scroll down this list, the sequence, and I will reach here, which says, you know what, you've got about 251 part numbers out of the total sample of 720 that you looked at. These 251 account for almost 80% plus of total earnings and 80% of about quantity. So, instead of looking at 720 part numbers at the outset, we looked at these 251 part numbers. So that was the PQS analysis. And this is your dendrogram, your cluster analysis dendrogram. So if you see here, these parts, this dendrogram is like a skyscraper diagram. And I basically go down, 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 and I stop here. So it's called a cluster analysis dendrogram, and that gives me, these are all the parts. And so I take all of these parts. For each part, I will have a quantity and a revenue. I sum that up, and that will give me the total revenue earned by that part family, because they have very similar routings, and the total quantity of parts produced. So that is your dendrogram. So this was basically the analysis to form the part families and to pick the part families, right? So the next decision in the quick start approach is which part family do you work on, correct? Because after all, the goal is let's form a part family, but because we are using the quick start approach, which is kind of almost like value stream mapping, where you just follow one particular part number's routing, let's find a bunch of parts from the part family you chose, which have identical routings. So we basically said, you know what, between part family 1 and part family 2, part family 2 just has 24 part numbers, different part numbers. And so if we were to look at the flow of one routing, there's a good chance that any improvements we make will probably apply to all 24 part numbers in the family, as opposed to here where you have 229 part numbers, correct? So next step was, from this part family, you pick a part or parts with the same routing. So that's the next step. So that's what we have. We have part family 2. These are all the part numbers in that. And these were the parts that we chose, which we'll see in the next line. So that was the project scope. Pick a few parts in part family number 2 that have identical routings. So Nina basically, again, presented these results to management. She was having meetings with their team almost every week and conferred with me by email or phone when she needed to. But again, extremely good industrial engineer, very good personality, very driven, with a lot of initiative. So again, this is for each of you to say, I can do this, and I can assure you, if you did this same type of scope of internship work, you will be successful. Okay, so we chose these parts, and management said, you know what, why? Because they predicted an increase in sales volume in the next fiscal year, which was 2006. And also within that part family, just these 3 parts identical, They account for about 15% of the revenue. So it was like, okay, let's go work with these parts, right? So once we've got these parts, the next step in the quick start approach is you obtain the layout of the facility and locate receiving, shipping, and all the other value adding work centers. So this is your routing. You can see again 19 steps. Each work center for each step is specified. There's a work center name. And essentially what you're doing now, like you were taught probably in the second lecture of this class, we're going to basically create a flow diagram. Why flow diagram? Because it is the simplest map that you can have of the flow of a product. And if you find that the layout of the facility is a culprit in bad flow, the flow diagram very quickly gives you a sense of what needs to be done. So you don't really need to create a value stream map. There is a role for value stream mapping when you get into high mix environments or even in any manufacturing facility, but it takes so much more data collection. And management sometimes are asking interns and consultants, show us what you can do. And it's almost like a weekly demand for show us why we are paying you. So with the flow diagram, you can quickly point out various ways, obstacles to visual line of sight. There are lots of good things you can see with just the flow diagram. So what you need for the flow diagram is a layout of the facility that shows all the work centers in the fast input file and this particular product's routing. And you need to know the specific work centers that this part goes through. So now you basically go and create the flow diagram. So bear with me, please. I will walk you through every one of the steps, and you can quickly see how nightmarish is the flow of products in a facility which has monuments. So when factories have not been designed for good flow, they can do automation and lean and Six Sigma till the cows come home. In fact, any other animals, because today with the COVID crisis, pigs won't come home because those plants have been closed. Cows may not come home because those plants have been closed. So what other animals can come home? Chickens, goats. So my point again is that if your factory is not built for flow, your efforts to do lean and Six Sigma and operational excellence are going to be half-assed. So let's track the flow of the product. Okay, so here we are, work center 951. That goes through the step number 2 is at work center 760. Then it goes to work center 510. Then it goes to work center 810. Then it goes to work center 80. Then it goes to work center 510 again. Then it goes to work center 310. Then it comes way down here to 673. It goes across to 666. Then it goes way across here to 952. Then it comes back to 520. Then it goes back to 310. Then it goes up here to work center 800. Then it goes to an outside process step, another outside process step, comes back to work center 570. Then here goes up to 958. Then 952. And finally 820. So you don't need to be a rocket scientist to know that the material flow just for this one part in a part family of 24 part numbers is so horrendously inefficient. And so what you do now with this flow diagram, so again, in the quick start approach slide, some of the bullets that I've put are, you look for flow delays. You look for the 8 types of waste. You look for the violations of the three principles of design for flow. There was a separate lecture on that. You look for the absence of line of sight. So what is line of sight? If I'm standing at work center X and the product has to be sent to work center Y for processing, do I know that work center Y is ready to get the work I'm sending to them? So while standing at X, looking in the direction of Y, can I see work center Y? Can I see its status? Can I see its operator? Can I see its availability light? If not, the line of sight is zero. If I can, the line of sight is one. What else does the flow diagram help? You look for cross flows and backtracking. You saw how many times certain work centers were having to be visited, but they were being visited from work centers which were way far away. Then you look for large travel distances. Think of it. Why do you have one piece flow in the Toyota assembly line? Because the next work center after the current work center is at most 6 to 10 feet away, clearly connected by a conveyor, clearly visible. Does this flow diagram indicate just with one part's flow that there is visual connections between various work centers? So, what really do industrial engineers know that they can do better? Remember, we talked about from to charts? Well, you could take 250 part numbers, create a from to chart, and then you could map the flows in the from to chart the same way that we mapped the flow of one product from work center to work center. Once again, if you see big, heavy float arrows without line of sight, there's an issue with how lean the factory is going to be, how much less delay you will have. So once the flow diagram is obtained, then the challenge is how to understand the actual delays and other forms of waste that are occurring. So the next step is to create a flow process chart. The next step is to now actually go and track the dynamic movements and delays of this particular order. So that was the next thing which Meena did. So she analyzed the flow diagram, and you can see again that very large travel distance. So you see again, here's my reservation. It is nice that, as industrial engineers, we go and compute the travel distance, but what is the economic value? What is the measure of cost associated with distance? Nothing. You have to convert that to things like line of sight. You have to convert that to batch sizes. Okay, you have to convert that to operator motion waste because people don't know where forklifts are that they need to pick up a batch and move it to another location. But again, with the flow diagram and the flow process chart, it was very clear that the number of value added steps was much less than the number of transportation steps. There was absolutely no line of sight because, work was being done in different buildings. And within each building, different sections of the building were separated for, dust containment or noise containment or heat containment. And then most importantly, because there was no line of sight, there was no communication. And, when there's no communication and there are no visual signals, you cannot have just-in-time material flow and good shop floor control. So the flow diagram is intended not to just scare management. The flow diagram is intended to quickly tell management, look, these are all the reasons why you have waste. These are all the reasons why you have delay. These are all the reasons why you have poor machine utilization. These are all the reasons why people are idle. Okay, that's important. So that was the flow process chart. Again, you've been taught this. So you know again that the flow process chart is the next enhancement of the basic flow diagram. And then after the flow process chart, you create the value stream map as the next enhancement of the basic flow of a product. So this histogram which you see, if you're familiar, these are all the basic activities that we typically do when we move a product through a facility. There are operation steps which we think are value adding. There are inspection steps which we think are value adding, but the rest of them, administrative steps, information flow issues, material handling issues, batch production inventory issues, waiting issues. So this is again, let me show you the process flow chart. So you're familiar with this, I'm sure. flow process chart. And when we did the toast Kaizen, uh, I'd shown you an example of the flow process chart we had created there. So again, please connect industrial engineering, your textbook learning, to the practical learning of lean. They belong together. The textbook misses things, the lean tools taught by practitioners miss things. In your position, combine the two bodies of knowledge, and you're just so much better an industrial engineer. So this is again what Nina did. She now picked up an order, an active order, and then either followed the order herself or she asked operators, supervisors, the person, Greg Muniak, that she was working with, look, can you please tell me the individual steps that when I look at the flow diagram and I'm trying to flesh it out and understand all the other activities besides transportation that unfold every time that this part is made, could you please help me to describe the details? And how do you do that? You basically create a flow process chart. So step one is unload material from truck, place in designated space. It continues. So, you can I'm just scrolling through the flow process chart. If you're interested, I'll be happy to send you the presentation and the process chart. So that's the flow process chart. So again, why do the flow process chart? Because you're trying to now grab more information that the flow diagram does not capture. The flow diagram gives you a sense of poor material flow. It gives you a sense of lack of line of sight, but the flow process chart enhances that information and puts it into distance, time, cost, and non-value added activity. So we saw that there were 28 transportation activities and 25 operations activities. I mean, that's too much. That's too large a number. Okay. So once the flow process chart is created, then you create the value stream map. And the value stream map that Meena created, the purpose was not to get too caught up with takt time calculations, because we knew that there's going to be no takt time. This is a pure make to order facility, and you cannot really apply the simple improvement methods that the book Learning to See teaches. But the beauty of the value stream method is that it takes the material flow, but it also puts all the processing data. Once again, whatever the flow diagram tells you, whatever the flow process chart tells you, the value stream map kind of enhances that, as long as you're working with a few products. So you have a material flow portion, you have the performance. So if you tracked a particular order, either if it was complete or in process, you can now say that at these points of flow, it was non-value added time. At these points of flow, it was value added time. The most important purpose of the value stream map is to capture the production control, shop floor control, scheduling activities, how they're doing it today. How do they tell individual work centers what to do? How do they know what orders to release? How do they communicate with vendors? How do they update the daily schedule at the end of each shift? So that is what the value stream map was very helpful for. And again, it helped Meena to present a complete diagnostic of the current state. But what was very important, basically she was able to say, look, when I looked at the flow of this particular part number that I'm tracking, and I did not even include the materials delivery portion of the lead time, the value added ratio is pretty much just 18%. So only 18% of the total time that this part's previous order spent being made was actually, it was being processed. The rest of it was basically non-value added time. So that is what the value stream map does, that it adds another layer of information, especially the production planning and control aspect of managing a production system. So again, more information. It captured the flow of information between departments, between the floor and the scheduler, even between consecutive machines. It captured the waiting times, which kind of translates to work in process inventory, and clearly showed there was no direct communication between departments besides the MRP system. So they waited for the MRP system to tell them what to work on, when to work on. Okay, so here was the problem that Meena basically pointed out to management, that once the parts are completed at any workstation, their status is input to the MRP system. So the MRP system assumes that once they updated the paperwork, that somebody came and moved that part physically, that batch, to the next work center. And there was no guarantee of that. So the MRP system, you can see, is completely detached from the reality of the flow. So again, management wanted to know, give us a better sense of where all the inefficiencies and delays and wastes and costs and irrational behavior and difficulties in communication are occurring. So this is the next thing which you as an industrial engineer should do just by following Nina's lead. She tracked the orders. Okay, she actually, so day by day, she tracked the order and tried to get a sense of where is this location. So that means there's the date, its location, what was the quantity? Was it a split batch? What was the condition of the part with respect to the work center it was at? And then some comments, like what is being done. And essentially, you can see again that the part flow tracking data that is being documented is like an enhancement of the information that typically ought to go into a flow process chart. So my advice to you again is that go ahead and ask yourselves, how could I create a more advanced version of a flow process chart for my internship? You don't have to be limited to what Mikhail Gruber's book or Richard Luther's book discusses. Today with what Excel can do and what Tableau can do, I mean, you could enhance the information you collect. But once again, you can see that here Meena had to manually track the parts, right, and its status. Today, with things like machine monitoring systems, with ERP systems and barcoding, you have to ask where you work, hey, can all this technology help me to collect when our orders are moving and when they're not, and when they're not moving, why? So at least I know for CNC machine shops, machine monitoring systems are a major technology that they should be exploiting much more than they do. So this was the parts flow tracking, which was purely based on time studies and observations. You can do videotaping, but again, understand people get, you know, nervous when they see themselves being videotaped. Until you go to them and say, look, this is how I use the videotape. And once they see that the videotape and the observations are being done with a positive end result, they will start becoming participating. So what did the parts flow tracking again show? From the flow of parts, there was a lot of waiting. And why was there waiting? Look at this. So if you did like a 5 whys and you had to go back and do root cause analysis and understand which of these problems should be the one to work on, you have everything: man, materials, methods, machines. This was the process. Once you hit a part on a forge, a hammer, it needs to cool down. Okay, employees are missing. So what they were saying was the waiting occurred for all these reasons. And trust me, these will probably be the reasons you will see wherever you go to work. The important thing is, what do you do with these reasons? And my advice to you again is, once you create the 5 whys chart, once you create the fishbone diagram to understand, here's the waiting at the bottleneck machine, try to quickly get management to agree on what needs to be done from the fishbone chart, for example, discussions, to start making improvements to eliminate the waiting time. Don't get too caught up with pretty charts, which is what Six Sigma, encourages you to do. Get to action, which is what Lean encourages you to do. So again, more information about parts flow tracking. You see, see this one. Sometimes the parts go missing because they have moved to the next operation, but this is not indicated in the MRP system. And sometimes when you say it's human error. Oh, I was busy doing something. I forgot to take the paperwork and update the MRP system. Or just maybe, well, the data entry station is 200 feet away. I was in a hurry to get home. My children were sick. I kind of forgot, right? Look, then there was a lot of overtime. Okay. Then there was no plan of where inventory should be staged. So whoever brought the parts didn't find space in front of the department. They went and put it someplace else. But they didn't tell the supervisor of that department, this particular order's parts are in that location. Now you see the importance of 5S. And there was no scheduling. There was no rule about which parts should be run first unless they were indicated as rush or hot or expedited. But those signals are basically saying this is a very wasteful activity. So when you do parts flow tracking and you have in your mind the 7 forms of waste clicking in your mind, and you have all these basic lean tools like visual management and 5S that you know about, again, what is the end result? You quickly get a sense of this is one of the root causes that we should be working on. Okay, so once you've created the value stream map, now it becomes the question, well, what do we work on to improve, right? So this is where you take the next step in the quick start approach, which is to say, look, we have developed the value stream map, we have done the flow diagram, we have created the flow process chart, we have walked the flows of the products. We know all the delays and wastes and costs. Okay, we know it all, but we need to focus on something, right? And I think that is where theory of constraints, which has this 5-step process, which you've already done, you've seen the goal video. It helps to focus your attention, especially if you think, what, in my job, in my internship, let me be focusing on one area which will have the biggest bang for the buck, then focusing on the bottleneck in a value stream is most advisable, right? So what have we done till now with the quick start approach? We took all their parts, we boiled that down to a part family, and we picked the part family which had most of its parts in the PQS sample. It was also small. We took representative parts from that family. We did the flow diagram, we did the flow process chart, we did the parts tracking, we did the value stream map. Now the thing was, okay, where do we go to improve? The bottleneck in the value stream map. So the theory of constraints, basically, the first step itself is you identify the bottleneck, and then you exploit the constraint. You basically say, what is causing the constraint to not be productive, right? Now, in a forge shop, you pretty much know what is the most important value-adding step and where typically you can expect the bottleneck to be, okay? We had a constraint that because we were funded by the Forging Defense Manufacturing Consortium, we had to kind of work on what was important to the forge shop. Okay, so you might see that we did not really work on the bottleneck as what was indicated, but that was our expectation from the sponsor of the project. So we had to identify the constraint. So what management said was, look, we know that the theoretical bottleneck is a vendor, sonic testing, okay? We know that the biggest delays that we suffer from are not in-house, they're with the vendor. But, we couldn't really go there, right? How can we go work with a vendor who might say, hey, why do I need to work with you? I'm under no contract with the government. I'm under no obligation to the Department of Defense. So sonic testing kind of blew out the window, okay? Ideally, when you work in such complicated shops, you should be trying to get your vendors also to be working in parallel with you, because that way there's going to be bigger gains across the extended value stream. Okay, now, the in-house bottleneck, they said, was the CNC machine shop, okay? Again, the theory of constraints, we would have gone through the CNC machine area. But again, because the grant had to do with forging, we kind of came back and said, you know what, CNC machine shop is a slave. If they do not get work, the right orders at the right time in the right quantity from the forge shop, then why call this SIFCO Forge Group? Call them SIFCO Machine Group, right? So even inside the forge department, we looked at the data collected, we looked at the observations, we looked at what employees said, we looked at what management knew, and it was like, let's work on these hammers, because these are the hammers that are used to make this particular sample of parts, and also most of the other 24 parts in part family 2, they run through these machines. So while we did not to the letter follow the theory of constraints thought process, we did basically come back and said, look, if Meena has to take the rest of her time with SIFCO for her summer internship and make improvements, give management the bigger picture about job shop lean, but also do something, let's do something where it matters. So why? These are the part family we are working on. These are the parts inside the part family that we are looking at in detail. And these are the two forging hammers that process most of the parts in the family. So let's go work on improving the performance and throughput on those machines. So these are the next few steps in the quick start approach, that once you've drawn the value stream map, you find the bottleneck, and now you essentially do theory of constraints analysis, exploit the constraint analysis at the bottleneck. So you look at the data, you look at why are the hammers not producing parts, and you come back and say why. You determine all the problems, you determine the most important problems, you look at what projects you need to do to attack those problems, and that's pretty much what you do. So pretty much that is the closure of the quick start approach. And now I'll just walk you through the details of implementing that focusing step, exploit the constraint step, and then once we found everything that needed to be done, then how did we narrow the scope of work that Meena and the team at SIFCO would do before Meena left. So exploit and elevate the constraint first, right? We basically improve the work assignments in the shop. So she had observed that, a lot of people were standing around at the various hammers. The hammers were not hammering, When the hammers are not hammering metal, you're not producing parts, right? So she basically did a time study. And again, it's a very involved study, but you can see that she essentially drew person-type flowcharts. She looked at the current operation at the furnaces and the proposed operation. And this is classic observation-driven industrial engineering. You might call that time studies, you might call that work study, but as you can see, this is it. This is where industrial engineering hits the road. And you've got to be prepared to work with the employees, and you've got to be able to say, all my observations, all my videotaping, all my man-machine chart analyses, all my standard work instruction efforts, they're basically going around to making you safer, making work easier, and not to put you under stress. So she did this time study analysis, and based on what she observed, she proposed changes in the employees' work assignments. And essentially what happened was, she did not say, well, with my recommendations, we don't need one person, fire them. No, this is what they use the person for. The extra worker will now be available to help in setting up the next hammer and loading the bar stock while the crew is working on some other hammer. It's basically set up time. So while people are working on a hammer, this other person will set up the next hammer, and then that crew will shift to that next hammer and start working on a job, and this person would have set the machine up. So again, keep in mind, please, in forging, keeping a part heated, keeping the die on the machine heated is very important. So having this person act as a coordinator, it was a big improvement. And again, Meena did a wonderful job. Wonderful job. I'm honored to still think that, 15 years ago, we were both learning, and she was an undergraduate, had done all her courses as a senior. She took these 2 courses from me, and boy, what a wonderful job she did. So again, continuing with exploit and elevate, the next thing was essentially cleanliness. So if you look at the photographs, the biggest issue was, forget about the place being dirty and dangerous to work in and, tripping hazards and things. We needed the queue of work to be set up in a very systematic way where at the machine, the next job to be run is immediately available. And, I will not go through the details of 5S, but this was another presentation that Meena developed for their team, and this was for the people who ran that particular hammer. So she made the observations, and then she gave them a brief lecture with examples of how 5S could be applied as a hammer. So I will simply walk you through these. You can stop the video and observe as and when you wish. So this is the state of the particular hammer. So again, there is no need to criticize anybody. The issue again is that why would you want your employees to be working in this environment? So go back to the first S in sort, right? Sort and then clean, correct? That's the whole idea, that you will not believe that in today's forging companies, you will not believe that even though the environment is a dirty process, they don't let the dirty process make the area dirty. So that's sort. Again, these were just pictures that she showed them as examples of what needed to be done. More details. So the biggest thing was, how do we arrange tools that support the setup of the hammer? But next work center, same thing, right? You can see it is so sad that, in manufacturing, management believes that it is okay for employees to work in such environments. Not fair, not fair. And many times, 5S, especially with safety and organization and management of the area for speed of work, those are such great ways to win over employees. More photographs of that hammer. So she was essentially giving them, okay, this is what the place looks like here at SIFCO, and this is what other companies have. Can we get to some point where we don't look like this anymore? So this was an example of how she standardized work between the hammer itself, the person who runs the hammer, and the person who helps the hammerman. Okay, so that's like a helper person. So trust me, standard work instructions and time studies, and it's still gold. It is still gold, no matter what people might say about robotics and cobotics and Internet of Things. Where there's a human being and a machine, there's going to be issues of what we call man-machine scheduling. You've seen that probably in the Toast Kaizen video, correct? That there were so many issues of coordinating the person, the toaster, the bread, the butter, the knife, and the plate. So imagine bringing that simple classroom example to bear in a complicated production environment. So this was some examples of standard work, and you can see details about each step. Self-discipline, very important, especially in a forge shop, which is a dangerous work environment. And some of the benefits that she presented to them. She said that, look, when I have been there, I've seen so many employees just looking for things. And, management asked the forge department employees, especially the ones who ran the hammers, is that the case? And they said, yeah, we wish we had things when we needed them. And this is again very important, the last bullet, fatigue and ergonomics problems. So that was again exploit and elevate the constraints. So that's the second thing which she did. And again, the goal was this one. Can we organize the queue of work so that there's some, remember in theory of constraints, drum buffer rope, the whole idea is that if there's a sense of how much work there is in the buffer, then you can subordinate the rest of the system so that the previous work centers are not pushing more work in process into the system. That was one of the goals of her 5S improvement suggestion. So once again, what's the ready pile for dies? These are dies which are ready to go for the job. Now you can see that they have so many dies that they just haphazardly kept both inside the forging department and outside. So once again, what is the importance of 5S and you're taking a course on, say, warehouse design? You apply the same principles to organize dies, right? So you will basically say those dies which are used most often should be easy to access. Those dies which are used least often should be at the back of the storage area and possibly kept on high-rise racks so that they don't take up too much floor space. So you see what she said, that she observed that there is a ready pile outside the Ford shop building because there is not enough space inside the building. And you again say why? And the typical thing is why? Because we are trying to make every part. We're trying to get business from a lot of customers. And as a result, we have to make a variety of parts. Because the parts are different, we have to have so many dies. So you can see again that this chart shows you all the travel that the die room, right? So this is where the dies are stored, correct? So look how this person had to walk. And now there's a RP is ready pile. There's one ready pile here, and there's one ready pile here. Then there's a polishing area. Polishing area is somewhere here, okay? Then these furnaces are all over the place, okay? Then the cleaning station is someplace here. Cleaning station is here. Yeah, I just found the furnace. It's here. And then welding, which is used to repair, is over here. So you tell me, as far as coordination between the material handler who serves the Ford shop, this gentleman, right, over here, and this gentleman who's managing dies, you tell me how timely and efficient is the setup, because the setup of a hammer basically means bring the die and have it ready at the time when the job is supposed to start. But if there is so much non-value added delay in the way that these two people have to work, it kind of becomes hard. So this was the current flow of dies. And then this was where she said that let's go do a Kaizen. And so they did this Kaizen in die logistics and storage. So you can see again that when she chose improvement projects, they were driven by the exploit the constraint step. And the exploit the constraint step was looking at the forging hammers which were being used, and especially those hammers which were being used to make these parts, which were focused on because they were part of a part family that had to be improved. So the whole effort that she went through was here. Improve the flow of dies to minimize handling and introduce systematic storage of dies to reduce delays due to retrieval, prep, and availability of dies in the Ford shop. Some of you have come from India and you've kind of, I think, worked in such harsh environments. And Ford shops remain a frontier of opportunity. So heat treatment facilities, Ford shops, electroplating. When you look for jobs, I know that today conditions are tough, especially for international students. But don't just limit yourselves to the big name companies. Look around you. In Houston, if you did say electroplaters, you will find dime a dozen. You look for heat treaters, you will find dime a dozen companies. They need help. Lean cannot be applied the way it's been applied typically in an automobile assembly plant. It cannot be applied the same way to these environments where the environments are tough, they are dangerous, and the process is pretty much batch oriented. Okay, so keep an eye open. Don't limit yourselves to who you apply for as far as work goes. Who knows? You just might get lucky. Okay, so this was the chart that Bina developed. Can you believe it? Just within 3 months, by talking to people, by herself discussing with the die room controller, with the die handler, she basically created this flow process chart. So here's how the process starts, right? So if you're saying, well, I wish to minimize the total time it takes to get a die ready, what do you basically say? Okay, let me attach myself to the die and let me see what are the different pathways of flow that the die goes through. So every step will have a yes or no, correct? I mean, for example, can you find the die in the ready pile? No. Okay. Find dies and bring to the die room queue. Guess what? Already you can see two forms of waste, right? There's a searching waste and there's a transportation waste, right? So imagine if you took all the no's in this flow chart, you will immediately find all the sources of waste. So you've done swim lane diagrams, you've done flow process charts, you've done flow charts, and this is a flow chart, right? You take the steps. What you might do with the swim lane diagram is you can basically map these blocks and diamonds onto the various departments. So that'll give an even better sense of how much communication problems are occurring between people in different departments or different locations. But she created this process chart. I think even the Synthesis teams developed this for their projects. And this is again gold. So when you look at die prep, you basically say, let me create the flowchart. And then from the flowchart, you identify the different wastes and the delay. So exploit and elevate the constraint. Uh, the next thing was, how do I improve the quality of the dies? So this is again a challenge. You know, people have to check the die, and if the die hasn't been found or the die hasn't been checked in time, how do they know that it needs to be repaired, right? So there were reworking issues, there were waiting issues. Uh, there was even other materials there. The die may be hot and ready, but have the materials arrived? So this was another thing which Meena came up with and said, look, as far as the productivity of the presses and hammers goes, here's the big issue with die availability and the quality of the dies. We again proposed the water spider. They said, yes, we'll think about it because they already had material handlers. Uh, Please think again that remember that this was us doing lean in 2005. Uh, Nina was new to it, I was new to it, and we really did not have much mileage under our feet as far as being able to tell people that look, the water spider is different from a material handler. A water spider is a smart material handler, and a material handler who has authority to tell people what to do when. And they are pretty cross-trained so that they're able to do many things. They know the dies, they know how to inspect the dies, they know how much repair work is needed. But we again pitched this idea to them, and we said these are all the advantages. And the good news is that 15 years later, in 2020, I'm able to confidently say, the water spider position is perhaps the most effective position I've seen in a lot of facilities where you take one of the better employees and you give them this combination of material handling and shop floor control and schedule execution authority. Makes a big difference. Subordinate the constraint, again, the whole idea was that once you know the forge schedule, then you basically tell the saw shop to cut bar stock and you tell the furnaces to be ready for, which parts they should run, correct? So the whole idea was that if we know the forge shop schedule, we can then schedule the saw room, the die room, and the trim makers to the schedule of the forge shop. We didn't get there. But again, you can see that by combining theory of constraints into the overall process of value stream mapping, you not only get to do all the improvement projects, but you also get to do at a high level the scheduling, the drum buffer rope method of scheduling. That may not be a very sophisticated scheduling method, but at the outset, especially if you're an intern or you're in the first 90 days of your job, it's something which you can implement. Okay. And the whole idea was that the forge shop should not have to wait. We should be getting maximum hit time from the hammers in the shop. We don't want unexpected downtime on the machines. Okay. And we would like these work centers which are supplying the forges, machines, to not be outrunning. So especially like the saws, right? If people are told, no, just be busy, they're just going to keep running the saws and cutting bar stock and creating piles of inventory of unprocessed part. And then they'll be looking for more work. So then they'll tell purchasing, hey, you got to buy more material for us to process. So purchasing goes and buys more raw material. What does it help? The saw basically is going to outrun the forge area. So subordinate the constraint is a very good way to do waste elimination, especially on the waiting and the work in process forms of waste. And then, of course, once you improve the forge department, then you maybe go to the machine shop or you reach out to the sonic testing supplier. So we didn't even get there. Keep in mind, again, this was just an internship. So next we did, for employee training, we had to look at 8 types of waste, right? So once again, we said, okay, why don't we just go and develop examples and share with employees and say, look, this is what waste elimination is. So next, Meena spent her time to do some of this effort in the SAW department and some of this work in the Forge department. She and I discussed and we said, look, what is it that we wish to present her data collection and observations? What was the format? This is what we came up with. So what we said was, okay, we know that there are 8 forms of waste, right? So in her spreadsheet, the first column is which waste, overproduction, transportation, weighting, whatever, okay? Then find some examples, right? Make a list of some of the examples of each type of waste which you saw. Why is that happening? And then how do you solve it? Okay, so you can see again that the amount of information she found in the SAW department was humongous. With what benefit? These are things which you can now invite employees to step up and work on. Okay, so at a high level, management works with the intern or the industrial engineer and they determine, okay, these are some employee projects which we can do. And then you say, you know what? Those employee projects are intended to eliminate certain forms of waste which are significant killers of profit and productivity. But they need to see this. Once again, as the industrial engineer, you are the best positioned to create this whole program and not only guide it, but help employees to implement it. So these were all the 8 ways which she found. Again, for each waste, examples, why they found reasons for that waste to occur, and what they thought would be the immediate action to be taken to eliminate that waste or reduce the waste. This was in the SAW room. Next, she went to the Forge department, did the same thing. Okay, so 8 forms of waste. The more photographs you take, recall again what I've always been telling you. It is not enough just to take photographs. You have to point to elements of the photograph to say, look, here's a safety hazard. Here's an ergonomic risk. Here's one of the 7 forms of waste. Here is a scheduling problem. There are no metrics. You have to point out to management and employees that what you see, they should be able to see. So it's no use just putting a photograph. It is important to give information from the photograph that now others learn and they say, okay, we can take it from here. Now we will do what you, as the in-house industrial engineer, showed us to do to eliminate waste. More, again, this was the Forge shop again. Amazing amount of work. It is just, I cannot say enough about her, 15 years later. But I've seen students in this class, I think, who are equally good and could do maybe better. It's just, you have to know what to do. And I'm just giving this example to you as something which each of your term projects could have been. But again, this takes a lot of on-site presence. We did not have that. So I did not want students to feel under pressure that they had to do the work of an intern. So all your projects are kind of like a fraction, a higher level version of the work that she did in her internship. This is very, very helpful. If you can go through this whole process, the quick start approach, and as you start looking at focusing on the bottleneck, this is what you can do. You can say at the bottleneck, when I looked at the subordinate step and I looked at the exploit the constraint step, these are the 8 forms of waste I saw. These are the instances. And these are all the things that we can do. Trust me, within about 3 weeks, you could be helping with a large number of projects, and each of them you could be tracking in terms of savings of time and dollars. So at the end of it all, what was the value? Basically, all of these projects were identified. Correct. So the next step in the quick start approach is, after you have performed the TOC analysis of the bottleneck, you identify and prioritize strategies for improvements, and then you schedule who will work on which improvement opportunity on which schedule. So all of these actions are basically described here, and there has to be, again, some quick decision from the employees and the management. Look, we've got 32 actions to be taken. Okay, come on, let's get real. We have to make parts also. Our customers are hollering on us to make parts. We can't all just be doing continuous improvement. So why don't we basically divvy up responsibility? And you can see again, this is when this work was done. So we had to basically classify all the projects on these two criteria. Okay, the level of difficulty and the amount of impact that they think the action would have on the company bottom line. So bear with me as I refer my notes. What I will do is, you've seen all these 32 actions, right? So I will read out those actions. So this is what they call impact versus cost type of grid. Okay, so it's again a 2 by 2 grid. So you can see that implementation is on the x-axis. Okay, so this side is easiest. So if I go in this direction, that is, it's getting easier and easier to implement an improvement idea. And if I go in this direction, it's becoming more and more difficult to implement the idea. So that's the implementation axis. And this is called the impact axis. Okay, so if I go in this direction, the impact is getting better and better. Okay, and if I go in this direction, the impact is getting lower and lower. So naturally, you're looking for everything in this area. High impact, relatively easy to implement. Now, a lot, theoreticians and academics will say, "Oh, you know what, this doesn't work," and management can bias the discussions, and employees can gang up and unnecessarily push their agenda, la di da di da. The point is, when you're trying to implement things, especially when you're an intern, I'm her advisor sitting 2 hours away in Columbus, she's in Cleveland, and we're trying to get something done, and we're trying to finish the internship with a decent guidance as to what they should do. This is pretty good to do, especially when it's being done with everybody that's going to be impacted in the room. And all we're doing is, people are basically being given a post-it, and they're being told, okay, this post-it represents this improvement action. Where do you think it should go? So if you look over here, this is what the group decided would be probably the best to implement. So what is action number 6? In the process of buying a new material handling truck, we need to take better care of them, not bang anything with it. So what they were saying was, look, we do a lot of material movement, and so many times the material movement itself is bad because the truck breaks down. It's hard to maneuver, and it hits the equipment at places. Can we just buy better handling equipment? Number 7, this one. That is, do 5S in the area of hammer number 2089 and check on the work that has been done to date for hammer number 2222 and the blacksmith area. So it was one like, okay, let's take the 5S orbit sheet. Let's go and see how well we did now that Meena has taught us what 5S should be. And then let's go look at the other hammer and go do a 5S. So yes, people might think 5S is so easy, big deal, it doesn't have. I think it's more a question of what objectives you set for the 5S Kaizen. That is more important. Next, let's look at this one. This is action number 1A. That is, purge the ready pile. So what they said was, look, we don't even know which dies we have used at all for how many years. So why don't we just please at least do this? Let's go and find out which dies should be in the scrap heap. Or at least say, okay, there are 2 sets of dies. Dies which we have used, maybe, and dies which we have never used. So please go back again when we had done the lecture on 5S and we had looked at the 5S at Boeing video. They looked at every item in their area and they made a decision, right? Three levels of decision. We use it. It needs to be in the area of work. We do use it, not daily, not often, but it needs to be in the immediate area of work so we can access it when we need it. And the third stage was, oh, we don't use it, this is junk, get rid of it, right? Same thing here. The whole idea was they just went around, they looked at every die in the two ready piles, and they sorted out junk, dead stuff, obsolete dies, and yeah, one of us knows that we did use the die, or oh, we use this die a lot. So this is basically, these were all the action items that were discussed upon. And then, of course, in the quick start approach, you have to schedule the implementation of different recommendations. So that's the last step. And you can see again that this is where, this is the area, and sometimes, too many ideas may get put in this area, but you've got to force people to essentially break. Maybe you can break this quadrant again into a four quadrant, and then force people to put things here, or here, or here, or here. So it's quick and it's effective, but it relies upon a democratic process of put your hand up, give your vote, show of hands, do we agree, let's go forward. So these were all the implementations. So from that chart, you can see that items 1A, 2, and 10 were in process, and they projected that die handling time would be reduced by 20%. Item number 3 got implemented. It increased awareness of, knowledge of what is where by the employees themselves. No longer were they always having to go to the supervisor and ask for information, right? Item number 11 is in process, and they targeted it for the first quarter of 2007. Item 15, 18 implemented. Launch schedule created for having tooling ready on time and in prime condition in die room based on demand for tooling in Ford shop has drastically improved the Ford shop schedule. They felt that they were being able to start on jobs on time. Okay. Item number 17 implemented. This continues. This was Greg Muniak. He was their lean champion. And luckily, we had him as a co-mentor with me for Mina. He knew that lean was needed, and basically he, how to say, managed interference with management and employees to the extent that by the time that Mina was about 2-3 weeks into her internship, she had the full support of the employees. So, and I think again, I give her full credit because she did not go in with this, oh, I'm going to find fault with everything. Her thing was more of how can I help you? And that I think is a very good message to lead. Help, not harm. Okay. So more implementation efforts. Item number 19 is in process. It kind of made the employees responsible for maintaining their work area. That's like a 5S audit. Item number 20, this was implemented. It reduced downtime in the Ford shop because what they did was they did preventive maintenance in the off shifts. So they did not damage actual production schedules. Item number 21 was in process. And I think this was the most important, that Greg was able to use Mina's work, internship results, to say, management, we need to hire a full-time manager. Somebody whose job is going to be, what improvements do we make? And when we do make the improvements, there has to be a clear payback to be justified. This driving lean through the organization is very hard, but it's needed. It's needed. And today, in the era of COVID-19, where we don't have that many people working, right? Because of distancing requirements, because of remote work requirements, it becomes even more challenging. But unless you have a full-time person who's always looking at, look, these challenges of working in a pandemic era are affecting our productivity, and here's how we should attack that challenge. Unless you have full-time people doing that, who best to have? Industrial engineers, So, hey, I'm in your corner, guys. I'm just saying, be able to do the work like, Mina did, and success will be yours. So this was a quote, because we were funded by the Forging Defense Manufacturing Consortium, we had to get these recommendations from every Ford shop we worked in, and the grant had begun in 2004. right? And this was 2005. So pretty much my funding was renewed every year. And the funding was renewed only when the manufacturers we actually worked with through this internship program came back and said good things. So in 2006, this was what the email that Craig sent to John Turpak, who was the director of the consortium, who then circulated that email to the Department of Defense. And here's what Greg said. Much of the initial work we have done is hard to quantify in terms of dollars, but we know there have been cost benefits both in pure time and dollar savings. But most importantly, it's in the mindset installed in the workers about looking for ways to improve processes. And he said, look, with the hiring of a lean manager, we expect to see large quantifiable cost savings. We should have the new person on board within the next 4 weeks. So hats off to Meena. I think that with all the work that she did at the end, with everything else that she did, besides all the Kaizans and data analysis, she helped this company to justify hiring of a full-time person. So that's my challenge to all of you. You have to, whenever you go interview, whatever you do, you have to basically be able to tell them that if you hire me, I will be able to do this for you. Everything from training to data analysis to implementation support. This is what I'll be able to do. These were again more general findings and suggestions. It's amazing how much she did. She just left everything in a report for their management. This is again kind of common sense, you know. I mean, we have an ERP system and we can't communicate, you know. Sad, but that's the situation. Imagine today, in the era of COVID, with social distancing and remote work, even more important, you have to ask, how is the ERP system? How are our smartphones? How are our electronic displays, machine monitoring systems, quality management systems? How are they communicating with each other? You know, and is the plant manager able to manage communications? How much do they communicate with supervisors, employees? So you can go through all these slides in your own time if you need to. More findings and suggestions. You know, I mean, this is commonplace. I mean, finding large travel distances between workstations and multiple handling. It's expected. And the suggestions were this one. The cold inspection area can be separated to define areas, so that there's ease of movement. And then basically arrange the products in the staging area, first in, first out, or by due date, or by size of die. It depends. This is where your warehouse design expertise comes into play. More findings and suggestions. Like I told you, water spiders, most important. And today, again, in the era of COVID-19, go and Google autonomous mobile carts, go and Google autonomous mobile robots, and of course, autonomous guided vehicles. Go and Google these terms because they are essentially automated water striders. Okay, and now what you're doing is you're just putting a person on board these devices. Okay, so now you have a man-machine combination, but I am sure that this particular position, the combination of robot and person, doing all material handling and logistical support in small and mid-sized factories is going to happen. It's going to happen. Standards. We talk about standard work instructions. Once again, I mean, unless you know what work is being done, how will you create the standard work instruction? So I was kind of disappointed with what the students submitted with regard to the standard work instructions for those Kaizen. You pretty much just copied everything from the solution key and gave it back to me. I was hoping that you would have created more of a Gantt chart representation with quality comments, safety comments. But please, again, take knowledge of standard work instructions seriously. Try and do some self-study. More findings and suggestions. The finding was there was no allocation strategy for matching a furnace with the type of heat treatment for a job. Oh, this is big. This is big. Why? Because heat treatment is another frontier for lean. Okay. So what was the observation? That there are many furnaces There are many furnaces that can perform multiple heat treatment processes, but there's no clear knowledge of which furnace can do which process. So, what's the loss? There's a loss of energy. There's an energy cost, right? Because furnaces burn oil or electricity, and the more that one furnace is not heating because it's going through a setup change process, you lose money. So while I have not been able to do this project, uh, I would love to have some student volunteer. Maybe next semester, if this course runs, we'll reach out and ask for heat treaters locally. And the challenge there is, you see, you want to create a matrix to match each furnace with a planned set of heat treatment methods. So a furnace can be set up to do a certain type of heat treatment step, like annealing or quenching or stress relief. So when you are more planned about which furnace can do what process, then you can assign specific furnaces to do a certain range of heat treatment methods, and thereby you reduce changeover time, which then translates to idle time, loss of energy, and then loss of throughput. Again, this is what Mina did. She got together with all the management and Greg Mooniak and others, the employees, the furnace operators, and she created this matrix. So across the top, you will see all the types of heat treatment processes, right? Over here, the different furnaces they had. And then for each furnace, there were the materials which were preferred to be run and what type of heat treatment capability they wanted on that material. And this is again a very random matrix. So again, if the course runs, there's a method called matrix cluster analysis. And depending on which teams may be interested, remind me, maybe we could work on this matrix, and I will reach out to this magazine Heat Treat Today and see if they may have a reader, one of the heat treaters in the country, who might give us the data to help them to kind of determine what are the preferred heat treat processes to be run on certain furnaces. So this is again a frontier. I'm not much aware of it, but the whole idea of setup reduction on unfriendly processes, so electroplating tanks, heat treating furnaces, painting booths. Oh, that's again tremendous opportunity for industrial engineers. This was the future work. Systematic handling analysis, I did not teach it in the course, but once again, there's a whole science of finding the right equipment to move the right material, the right time, in the right container, in the right orientation. There are 8 principles of good material handling. And when you did the flow process chart, and when you did the flow diagram, when you look at all transportation steps, either manual transportation or equipment aided transportation, that's where you would use systematic handling analysis. This is the work of Richard Luther, who also developed the facility layout planning method of systematic layout planning. Extremely knowledgeable person, but a lot of his work and ideas would be kind of out of date in the 21st century. This was very important, process rationalization. We did not know when we looked at different routings if all the steps were necessary and that all the steps had to be performed. So it's no use doing flow diagrams when many of the steps you're mapping aren't even needed. But these things cannot be found out within an internship, within 3 months. It cannot. And this was also again a big goal from a scheduling perspective. Can we have it such that when I look at any of the hammers, it's got a job in process and it has a job ready to run on that. So having the next job available in the hotspot in case something goes wrong. So the point again was that if something goes wrong with the particular job I'm running, I can remove that job and retool that hammer to run the next job. So +1 is a scheduling holy grail. If you can do it, it represents a very quick response organization overall. So that's pretty much today's lecture. Any questions? I don't see any chats. Well, I see pretty much everybody was present. So this, I will take this opportunity to thank you guys for tolerating me for a full semester. I see that most of you have done a very good job on your assignments. Again, uh, I will take care of your grades. I do feel that a couple of teams did not come through on their assignments completely. It was a little disappointing, but again, these are very challenging times, and grades are not intended to be a weapon. So if you have questions, please email them to me. I have sent out your resumes to several companies that have contacted me. Solarcraft was the latest. Let me know if I can be of any help. Okay, I'll see you guys. Thank you. God bless.